All right, let's dive right into this explainer and embark on a totally mind-bending journey. We're going to see if humanity can actually, literally break the universe's ultimate speed limit. I mean, for generations, we've all looked up at the stars and dreamed of traversing those vast, impossibly empty gulfs between them, right? But dreaming is one thing, and the harsh, unforgiving realities of physics are quite another. Today, we're exploring the cutting-edge theories that suggest interstellar travel might actually, mathematically, be possible.
So, could humanity ever travel faster than light? To answer this immense question, we are throwing out the Hollywood magic. We're going to look strictly at the peer-reviewed physics and theoretical math that separates science fiction from real, hard scientific reality. We're diving into the actual equations and the general relativity frameworks that top astrophysicists are actively debating today. Ultimately, we want to know, is a warp drive something we can actually build, or is it just a mathematical mirage? You know, the legendary Isaac Asimov once said, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny." And this brilliantly illustrates exactly how physicists feel when they look at the mathematics of space and time and discover these astonishing loopholes. Science doesn't always advance with a sudden stroke of absolute genius. Usually, it advances when researchers look at established equations, like Einstein's, and notice weird, unintended consequences that really shouldn't be there, but absolutely are. Okay, let's start with Section 1, the cosmic speed limit.
Before we can even talk about breaking the rules, we absolutely have to understand the impenetrable barrier that holds our universe together. We need to look at why light speed is considered the ultimate unyielding limit, and why traditional rockets will never, ever get us to the stars in any reasonable time frame. The sheer intimidating scale of space is our first huge hurdle. To put things into perspective, even if we hitched a ride on our fastest man-made object, the Parker Solar Probe, it would take us 65 centuries just to reach our closest neighboring star system, Alpha Centauri. That is 6,500 years just to reach the house next door in our cosmic neighborhood. So yeah, standard propulsion simply is not going to cut it.
And the ultimate roadblock here is Einstein's special relativity. According to this rule, as an object's speed accelerates and gets closer to the speed of light, its mass essentially grows without bound. What this means in practical terms is that it would take literally an infinite amount of energy to actually push a physical object to the speed of light. And since infinite energy doesn't exist, moving through space at light speed is strictly, permanently forbidden for anything with mass.
Which brings us to Section 2, loopholes in spacetime.
So, theoretical physicists have actually found a massive loophole around this cosmic wall, and they did it using the framework of general relativity. If special relativity is the rulebook for objects moving through space, general relativity is the rulebook for how space itself behaves. And it turns out space is far more flexible than we ever imagined. The crucial takeaway here is that while nothing can travel through space faster than light, space itself can expand and contract at speeds far exceeding light. We already observed this. Cosmology tells us that parts of the universe are receding from us at faster than light speeds because the universe is expanding. Space itself has absolutely no speed limit.
To picture how we might actually harness this, imagine standing on one of those moving walkways at an airport terminal. You aren't taking a single physical step, right? You aren't expending any energy to move your body through the local air. But the belt of the walkway, in this case space-time itself, is effortlessly carrying you to your destination at superluminal speeds. In a local sense, you are completely at rest, but globally, you are moving incredibly fast.
And that leads us to Section 3, the Alcubierre Warp Drive.
This exact conveyor belt mechanism is the foundation for a concept proposed back in 1994 by theoretical physicist Miguel Alcubierre, which literally brought the warp drive out of science fiction and straight into mathematical reality. He proved that Einstein's equations technically allow for a localized distortion of spacetime. The drive works by manipulating the geometry of space to create a bubble where the interior remains a completely flat, inertial reference frame. This is absolutely crucial because it means the crew inside wouldn't experience any crushing g-forces and they wouldn't suffer from relativistic time dilation. The ship just sits perfectly still while the space in front of it collapses and the space behind it violently expands.
Let's shift gears to Section 4, wormholes and cosmic shortcuts.
Because warping space isn't the only mathematical trick up our sleeve, we also have to consider Einstein-Rosen bridges, better known to us as wormholes. If a warp drive is like a conveyor belt, a wormhole is like folding a map of the universe in half so that two completely distant points touch.
Unlike a warp drive that rides a wave across space, a traversable Lorentzian wormhole fundamentally punctures right through space-time, creating an instant shortcut between two isolated cosmic regions. These structures could theoretically be large enough to accommodate human travelers, acting as physical cosmic bridges.
But, and it's a huge but, keeping a wormhole open is a monumental physics challenge. To keep this theoretical tunnel from just collapsing instantly under its own immense gravity, calculations show it requires an incredibly delicate, perfectly balanced interplay of hydrostatic and anisotropic forces. And the crazy part? The only way to achieve this outward-pushing stabilization is by fueling the wormhole with something called exotic matter.
Which brings us crashing back to reality in Section 5, the enormous scientific challenges. Yeah, before we start packing our bags for Vega or Alpha Centauri, we really must confront the terrifyingly colossal physics problems standing in our way. The math might allow these structures to exist, but the engineering requirements currently read like a total cosmic nightmare. The original math for the Alcubierre drive demanded an impossible amount of negative energy, an exotic substance that literally violates standard energy conditions. To power just one warp ship, you would need more negative mass energy than currently exists in the entire observable universe. It's a staggering, effectively impossible requirement.
And the bad news certainly doesn't stop there. Even if we somehow magically found this negative energy, the sources warn of some pretty lethal side effects. As the ship travels, it would accumulate infinitely blue-shifted high-energy particles on the bubble's leading edge. Upon stopping, it would unleash an apocalyptic shockwave that would literally vaporize the destination upon arrival. Meanwhile, Hawking radiation generated by the bubble would simultaneously fry the crew inside. Oh, and as a fun bonus, you might accidentally create a time machine that completely shatters the laws of causality, so lots of problems to solve.
But don't lose hope yet. Section 6, the future of interstellar travel. Okay, let's dive into this final chapter, because despite these apocalyptic hurdles, recent breathtaking discoveries are actively rewriting what we thought was completely impossible. Science doesn't just stand still, right? The equations are constantly being refined by a new generation of physicists who refuse to give up on the stars. We're witnessing this incredibly rapid evolution in the mathematics of interstellar propulsion. We are moving from totally impossible theoretical requirements just 30 years ago in 1994 to highly tantalizing modern solutions today.
Just look at this progress, it's absolutely staggering. Back in 2012, NASA-affiliated physicist Harold White realized a genius geometric loophole. By modifying the shape of the extremely thin warp bubble into a thicker, fuzzy torus, think of a donut shape, the required exotic mass just plummets. Instead of needing negative mass the size of the planet Jupiter, White's math brought it down to the weight of the Voyager 1 space probe. That is just about 700 kilograms.
And it gets even more stunning. In 2021, physicist Eric Lentz discovered another mathematical loophole using superluminal self-reinforcing waves called solitons. His peer-reviewed research showed that you could theoretically generate a warp bubble using normal, purely positive energy. This is a massive, real game changer because it completely eliminates the need for that impossible exotic negative matter, pulling the physics out of the realm of pure fantasy and back into conventional, albeit extreme physics.
So, what you should really take away from this whole explainer is this. While we are definitely still centuries away from building an actual warp drive, the scientific consensus has fundamentally shifted. We've gone from "it's completely impossible" to "it's an enormous engineering challenge." The universe's speed limit remains, but the fabric of space is ours to bend. So, looking at the unbelievably rapid mathematical advancements we've made in just 30 years, what do you think humanity's first step into the wider cosmos will actually look like?